Alrighty then. This is where we introduce the second law of thermodynamics on this plate. And let's see. No, I get rid of that. Anyway, on this plate, we see here that the driving force or the thing to look at as far as spontaneity of any process in the universe is to see whether entropy is created. If entropy is created or predicted to be created in a process, then thermodynamically that process is said to be spontaneous. Now, when we apply it to a chemical reaction, uh, we're saying that it's product favored. Now, if we look at a process and we see that in that process, we would predict that there would be a decrease in entropy. Um, so, what does that mean? Does anybody want to take a stab at that? What does it mean to have a delta S that's negative? Um, all right, let me ask an easier question, hopefully. What does it mean to have a delta S positive or greater than zero?
Would it mean that you gain energy?
Oh, okay. Um, maybe in some cases, yes. But entropy, remember, is related to energy, but it's the amount of energy that's needed to, be put into something so that it exists at a certain temperature. But really, our definition of entropy, remember, that's the number of ways that energy can be dispersed in an object. Um, and so we connect this quality of entropy to uh, the dispersion of energy and or particles. And Einstein said, well, you know, energy, mass is energy, so it's kind of the same thing. So when delta S for a process is positive, that means that there's an increase of the number of ways that this energy can be distributed. Um, and so, according to this second law of thermodynamics, that process is favored naturally. In other words, you don't have to do anything about it. It's just going to take place. And we don't know how fast it's going to take place. That's the study of kinetics will tell us how fast. So we're just looking at the kind of off and on switch in which direction processes are predicted to take place if left alone. So if I look at a process and I calculate its delta S and it comes out positive, the second law of thermodynamics says that that process is spontaneous. Correct? Do you understand that?
Yes.
Okay. So what does it mean if I calculate that delta S and it comes out to be negative?
That it's not favored and it wouldn't be spontaneous.
Yeah, that's correct. And even further than that, you can say that the opposite process would be spontaneous. Because you remember one of the thermodynamic quantities we found before when studying enthalpy, H? If you changed the direction of the reaction, for example, that changed the sign of delta H. And it's the same thing with S. So if I say that a process is non-spontaneous, as written, they say sometimes that means as written, you define the reactants on the left of the arrow and the products on the right. If it's non-spontaneous as written, let me see, maybe I can write this out over here. So I have reactants over here. Reactants go to products. And if the delta S for this is less than 0, then you're right. We would say that's non-spontaneous, but it implies that if I took these and I made those the reactants in this new equation, that delta S for that would be greater than 0. And so the opposite is spontaneous. Another way to think about this is our analogy with a boulder on a cliff. We know that eventually that boulder is going to end up in the valley, right? But you'll never see that boulder go from the valley and jump up on the mountaintop or on the hill. So there's even more implied when we study the signs of these thermodynamic properties. And you shouldn't lose sight of that fact. It's a two-way street, and we know that from studying equilibrium. All right, so we may not have mentioned that last time, but it's implied. And until you study this and think about it in all the different directions, you might miss these subtle facts that are buried in equations like this. So to sum up, if something is predicted to be non-spontaneous in one direction, that implies that it's spontaneous in the opposite direction. Okay. All right. So anyway, we introduced this equation, the second law of thermodynamics, and the equation that embodies that second law. And we used it to explain an apparent contradiction to what we understood at that point, which was that things take place to reduce the amount of energy, right? And I think that's what you were talking about. But it's different from that. I mean, energy is definitely tied into it, but it's really this idea of entropy and the many different ways of spreading out that energy. Because, you know, spontaneous processes are not always accompanied with a reduction of energy or giving off heat energy, for example. And so we were able to explain this endothermic reaction in terms of energy last time. And we said that, well, this guy's going to absorb heat from the surroundings. So the entropy of the surroundings must decrease because we know how entropy changes with temperature. On the other hand, we have this process where I take a solid and I make an aqueous solution and I spread out those particles. So the delta S for the system is positive, but the surroundings, the delta S of the surroundings, we predict to be negative. And then we said yesterday, well, then why does this process take place? Well, if we use the equation for the second law, I think you can see. So this delta S that's negative for the surroundings goes in this position. The delta S that's positive for the system goes here, yet we know that when we add those two up, this has to be true for a spontaneous process. So therefore, in this case, for this reaction under these conditions, room temperature conditions, this term here must outweigh this one. So this is smaller in magnitude and negative, and this is larger in magnitude and positive. So it wins out, makes the delta S of the universe positive. So this reaction is spontaneous. Is that clear?
Yeah, it kind of makes sense. I think I'll have to do some more reading on it.
Yeah, well,
Yeah, same here.
you can read it, and hopefully, if you go back, do you ever go back and watch these and try to understand what I'm saying in super slow mo?
Yes, I do at least.
Well, do you
Yeah,
think that helps?
yeah, it definitely does.
Okay, good. Because it's kind of, I'm going through this in my own mind, and I'm trying to share the logic that I'm thinking about, and hopefully it will connect and make it a little clearer to you guys. And if not, then maybe I should do something else. I don't know what. Yeah. So as always, if you have any questions, or there's like anything cloudy, please, by all means, stop me and ask me to do it over again and explain that one point and see how, we can cement any connections if possible. All right. So we applied this second law of thermodynamics to some reaction to see, what's going on. And we said, okay, let's take a look at this reaction where we make water from gaseous hydrogen and oxygen. And we're going to apply the second law of thermo. Okay, so we need to calculate a system delta S, which we know how to do now from the third law of thermodynamics, which sets the standard of entropy for everything at zero under specific conditions of zero temperature. So we can look at those published values in your textbook or online, sum up the products, subtract the sum of the reactants and all their entropies, and calculate a delta S for the system. And maybe, when you're going over your notes, you can go ahead and calculate this from your book values, and it should be that value or pretty close to that value. And like we mentioned last time, if it's not exactly that value, that's okay, because there's different experimental groups and they have different precisions, different standard deviations. And published values in textbook might be an average of a bunch of research groups too. They don't really tell you where exactly they got those values, or maybe they do, but you got to dig around for it. All right, so you can calculate the delta S for the system. Now we have to deal with delta S of the surroundings. How are we going to calculate that? Well, to do that, we can use the equation that we introduced previously, the one for specific conditions of constant temperature. And that's good for the surroundings in most cases, because the surroundings don't, there's, they call it a big heat sink. There's a lot of available energy there, or it can take a lot of energy, and there'll be negligible change in the temperature. So that's what they mean by a large heat sink. And that's what the surroundings is in most conditions, like the conditions in the lab. You know, if you mix two chemicals and it's exothermic, so there's heat given off, but the temperature of the lab doesn't change from that heat. It's negligible. So it's a constant. So we can employ this delta S surroundings in a lot of our examples because of the fact that the temperature doesn't change. So once we do that, we can say, okay, well, there's the conservation of energy. So heat into or out of the surroundings has to go into or out of the system. So we can say that Q surrounding equals minus Q of the system. And so I know that Q of the system can be related to delta H of the system under constant pressure conditions, which is again what we experience in the laboratory when we do experiments and the beakers are open up to the atmospheric pressure. So I can use this analogy and say, therefore, that this has to equal minus Q, sorry, not Q, delta H of the system. And so that's where this term comes from. All right. Now, once you understand all that, then I can again find the delta H of the reaction and calculate that using our formula for summing up the delta H of formations of the products and subtracting out the delta H of formations of the reactants, and estimate that value and calculate my delta S for the surroundings. And this is kind of a prelude to how we take the second law of thermodynamics in this form and reformat it to a form that focuses just on the system because of these type of arguments and these type of analogies. All right, so anyway, we'll get to that in a second again. But then we went on and we calculated what the delta S of the surroundings would be because of the heat that's given off in this exothermic reaction. And we see that the delta S of the surroundings increase because of that exothermicity. And we can look back to the equation or the reaction that we're calculating it for and say, okay, well, yeah, it makes sense that this is going to be positive because there's heat given off to the surroundings. And the system delta S we calculated using our equation, and we see that's negative. Can anyone out there, if you guys look at this reaction and tell me why you would predict the delta S for this reaction, or which we're calling system, why it would be negative in this process? Does that make sense?
Because it's not favored.
Yeah, but how would you know that by just looking at the reactants and their phases and the product and its phase and what you know about entropy? All right, that's all right. This is all new to you, so we have to go back to the definition of entropy, and you should do that as many times as you need to. So remember, entropy is this idea or this quality of the spreading out of energy and or particles. So look at this. Are the particles here on this side of the equation, the reactant side, are they more spread out than on the right.
Yes.
Okay, then the change is an increase or a decrease in entropy when I go from the reactants to the products. Is there more entropy in the products or less than the reactants?
Less
Less.
entropy in the product.
Yeah, there's less for the reasons we said, right? Because entropy is the spreading out of particles. And here we have liquid water. So in liquid water, or liquid H2O, you have water closer in proximity than you have the hydrogen gas and the oxygen gas. Remember, that was one of the things we looked at before when we were just introducing entropy. We said the entropy of um, solids is less than liquids and less than gases. Gases would have the most entropy because the particles are more spread out, right? So we should, I think, keep going back to that definition and making sense of the entropy values that we see. And yesterday we just went over it, and we just kept on going. But I think it's important to check along the way to make sure everything is logical and making sense. So that's just another thing you can check to see if you're understanding the concepts. Any questions on that? All right. So then we put those two values together. We saw that even though one of the values went down and one went up, when we add them together, there was a net positive. So the universe was positive. This reaction is predicted to be spontaneous as written, or in other words, to say that is it's product favored. So if we put hydrogen and oxygen in a container at room temperature, we would expect that condensation would occur, and that condensation would contain water liquid. We don't know how long it would take, but it will happen. Um, all right. Any comments or questions on that?
Can we say that this reaction is reversible because spontaneous?
Yeah, so you would say that this reaction is spontaneous and irreversible. And remember, a thermodynamic irreversibility doesn't mean you can't take water and make oxygen and hydrogen from it. We can. We know we can do that. You may have seen the experiments where you take water and you put it in a beaker and you put electrodes in there, positive and negative, and then you put an upside down burette over each one, or some sort of a glass tube, and bubbles will occur at each one of the electrodes, um, and you would collect hydrogen in one and half the amount of moles of oxygen in the other. So we know we can do that, right? We can reverse the reaction. But what it means to be irreversible is that if we did reverse it, it would cost us more energy to make these than the amount of energy that was given off in the process. That's what irreversibility means. So I don't know if that cleared it up for you. Maybe you have a follow-up question.
Oh, it's clear. Thank you.
Oh, sure. Thanks for asking. Yeah, so these terms again, are different than we use them in everyday language. Like spontaneous, we usually connect a time to that. So he did this spontaneously. That was, just jumped up and ran to the bathroom or something like that. But that is not a thermodynamic definition of spontaneously. That just means that it's going to take place without external influence. We don't know how quick it's going to happen. And irreversibility doesn't mean that you can't reverse it. It just means that when you do reverse it, it's going to cost you more energy than you could have extracted from the natural process. And really, that's kind of a key concept in thermodynamics, because things take place naturally. Wouldn't it be great if we could figure out what those things were and then extract all this energy that's given off from that natural process that takes place, like water flowing over a fall? We could put in a bunch of wheels, right? And turn those wheels, and then that'll turn copper windings in magnetic field and generate electricity, or a hydroelectric power plant. So you tap in to this natural occurrence, because there's going to be sometimes energy given off. And so you can see that's where we're going with this as scientists. We understand it, we quantify it with equations, and then we know the amount of energy that we might be able to extract from the natural process. And so that's where the term irreversibility comes in. It doesn't mean you can't go against nature. You can go against nature. It's just that you're going to be losing every time in the end when you total up the scores. All right. So we said, okay, well, that's great. We kind of understand why all processes in the universe take place, but hey, we want to focus in on chemistry. So let's take that second law of thermodynamics and the equation that comes out of it, and see if we can and look at another form of this equation. So we said, yeah, sure, we can. We can get rid of that delta S surrounding terms like we did before by equating the heat in and heat out. So Q surroundings equals minus Q system. Okay, so we can use that and get rid of the surroundings term and focus in on the system and what it does as far as heat in or out of the surroundings. Because if in most of our conditions, that's a big thermal sink, our surroundings, its temperature isn't going to change very much. So in Chem 200, we can use this simplified equation for entropy. So we do. And we get rid of that term. This term's already the delta S of the system, so that leaves us with the delta S of the universe. So last time we said, all right, we're going to make a new definition. And by making a new definition, we can change the equation of the second law that looks like this into something that looks like this, where all the terms are terms for the reaction or the system. Another thing you can notice is when you multiply S, entropy, by temperature, remember the units of entropy are joules per mole degree Kelvin. This Kelvin is a part of the entropy definition. And if we multiply by temperature in Kelvin, what do we get? We get a term that's energy. So we define this term in terms of energy, and we call it Gibbs free energy. Now, why do you think they call it free? What's that refer to?
Is it because it just happens?
Yeah, that's right. It just happens. It's natural. So when you find a process that takes place in nature and therefore it has to increase entropy, that um, is equated with a change in energy. And that's the amount of energy that you could use, like we were talking about, tap into. So that's why they call it free energy, because it's up for grabs. Now, you should also note,
Is that essentially like combustion engine?
yeah, it's anything, man. This applies to every situation. So that's the energy that's up for free. But like in a combustion energy, the amount of energy that's given off, um, you can only use a fraction of that free energy. This is like a maximum a bound, maximum. But you have to pay the piper. You have to lose heat to the atmosphere. You're going to lose energy to friction and so forth. So this free energy is a maximum amount. And sometimes this delta G is also equated to or described as work maximum. And so you'll see that that's the maximum amount of energy that you can use for work. But since, you know, there's always a loss, and this is another reason why you can't have a perpetual motion machine, is because of this loss. You know, you try to reduce friction, you try to reduce heat loss and stuff like that, but you can't get rid of it totally. That's why it's a maximum amount, but you can never attain that maximum. All right, any other comments or questions on how we went from the second law of thermodynamics for all processes in the universe to this Gibbs-Helmholtz equation that applies mainly for chemical reactions? Yeah, so it's all embedded in there. And so that's what we use now, this Gibbs-Helmholtz equation. And so last time we were just trying to get used to this equation, and we're saying, yeah, so if delta S of the universe is positive, then the process is spontaneous, which means that for that process, the delta G, if it's a reaction, has to be negative. And it's because of the way delta G is defined in terms of the universe. It's got this negative sign right here. Okay. And all those other things that we said are true as well. In other words, if delta G comes out positive, that means that process or that reaction is non-spontaneous, but the reverse is spontaneous. So it's got important consequences, the signs for which way a reaction's going to go. So it seems like to me that the sign of delta G is kind of like the Q concept in equilibrium. Q can tell you which way the reaction's going to go when you compare it to the equilibrium constant K. And the sign of delta G will tell you which way the reaction is going to go as well. So it's kind of like that relationship. Any questions on that? I know it sounds like, oh, these things are unrelated, but they're not. They're all related. All right. So now when we look at this Gibbs-Helmholtz equation down here, you'll notice that we dropped the subscript for system. Now, anytime you see this equation, you are to assume that it's talking about a reaction, and the reaction is the same thing as what we called the system before. Also, For most cases, these would have superscripts on them of 0. Does anybody know what that indicates? If I had the superscript of 0 here, here, and here.
No.
Okay, good. That's awesome because that means you're going to know now. That means under standard conditions. Does anybody know what standard conditions are?
Temperature and pressure, just
Yeah.
25 degrees and 1 ATP or
Yep. You got it.
atmosphere.
ATMs. Awesome. All right. Now we want to take a look at this equation again, this delta G equation, the Gibbs-Helmholtz equation, which is applied to chemical reactions specifically and tells us which way the reaction is predicted to be spontaneous. I'm just going to see if you guys got this yet. What does the sign of delta G have to be for you to predict that that process or that reaction is going to be spontaneous?
Negative.
Yes, it's got to be negative. Okay. And if it comes out positive, that means that that process is non-spontaneous as written, but it implies that the opposite is spontaneous, right? All right, so we want to get at that sign of delta G, and we're going to do that in a second, but I also want to bring this up. Now you have a magnitude of delta G, and that magnitude is the number. So I have some delta G and say it's spontaneous. So I have a negative and then some value, some number. So we refer to the sign, obviously, is out here. And this number right here is called the magnitude. It's just the amount. Now, you're going to see a lot of delta G values for processes or reactions, and they're going to have different magnitudes. Does that magnitude mean anything to you from our discussion today? What does that value mean? It's good. Well, what units is delta G going to be in, first of all?
Would it be joules per mole?
Yeah, probably, right? It's going to be joules. Joules per mole or whatever. It's going to be joules something. If you multiply it by the number of moles, then the moles cancel out. But yeah, it could be joules per mole. So it's energy. So what does that value? The bigger that value is, the what?
The more energy you have?
Yes, the more energy that's given off, right? And the more energy that's given off, let's go back here. What happens? The more energy that's given off, maybe the more work that you can extract from it and do something useful, right? So keep that in mind too. So there's an importance to the sign and also that value, okay? And any questions so far? All righty. Okay, so now we have a simple plot over here of energy on the y-axis, and then the reaction coordinate on the x. So this is nothing new. We've seen this before, okay? But we're talking about the free energy. And that's going to be inherent to any system or any reaction that's taking place. Okay. Now I can start out with just pure reactant, and I could calculate an energy content, and we can associate that with Gibbs free energy. Okay. And then I can do the same thing with just pure product. If I had a vessel of just pure product, I can calculate that. And then I can calculate or put it on an axis to show the relative difference between these 2 points. Right? And that would be right here for the reactants, and the products would be up here for their energy content. Okay. And as I change the complexion of that mixture, so the reaction starts, in other words, and I change the complexion of the mixture between the reactants and the products, the free energy content in that system changes. And I see in this picture that as I go to the right to this point, and I compare it to this point over here, I see that the Gibbs content is decreasing. Okay. And so that tells me that from this mixture of reactants and products to this mixture of reactants and products where there's a little bit more product, the Gibbs content decreased. So I get negative a number, right? And so that reaction is said to be spontaneous from this point, this initial point, to this final point, right? And that's going to occur all the way down to the minimum. But look, if I look from the perspective of the products, and I say, all right, I'm going to start with this complexion, and I want to look at the Gibbs free energy at, say, this complexion. I see that it's rising again, or it's rising. So this final minus initial is going to give me a positive delta G, which tells me that this direction is non-spontaneous. In fact, because of the positive sign, I can predict that the opposite direction is going to be spontaneous. I'm going to take this complexion of reactants and products and go towards this complexion where some of those products are converted back to reactants. So you see how this theory and these equations make sense as far as what side of the equilibrium you are on in any reaction, where the equilibrium now can be associated with the point of minimum delta G. That's as low as you're going to get as the change in the Gibbs free energy. And that's where a process is going to hang out. And even though that process may be dynamic, there's a net conversion of reactant to product and vice versa. They're going to be equal. And so it's at equilibrium. And so this point in our Gibbs energy content should be related somehow to the equilibrium mixture. And so that begs the question, is delta G related to the equilibrium constant? Any questions on that? Does anybody want to answer this? Yes or no?
Yes.
Yeah, you bet. You guessed it. So that's where we're heading. We want to take a look at the delta G and how it's related to the equilibrium constant. And this kind of exercise here, by looking at the free energy content for a typical reaction and how it changes during a reaction lifetime, or a reaction as it goes towards equilibrium. So if we start over on this side of the mixture, there's going to be a net conversion of reactants to products. And according to thermodynamics, if we start on this side of the mixture, then there's going to be a net conversion of products to reactants. And this is predicted by looking at the second law of thermodynamics, and specifically for chemical reactions, it's the Gibbs free energy content that we're concerned with minimizing. And in the process of minimizing the Gibbs content, there's energy up for grabs that can be used for doing stuff with it, work. All right, now having said all that, let's take a look at the signs here. Now, if delta G is negative, then the forward reaction is spontaneous, right? Just like we saw here. If delta G is 0, then we're referring to that minimum where there's not going to be any changes of Gibbs free energy because it can't get any lower. That's the one that we associate with equilibrium, that point. And if we go to the next point, when delta G is positive, that means that process in that direction is no longer spontaneous, but the reverse is spontaneous. It's going to go backwards. So all of those things have to be rationalized in the light of our Gibbs-Helmholtz equation. Now, before we go on, there's just one more little tidbit in here that maybe we can extract some info out of, and that's the magnitude of delta G. Okay? If I start here and go down to the equilibrium, then delta G is going to be this magnitude. But if I start from here, all products, and go to equilibrium, then the delta G is going to be this magnitude. So it kind of gives you an idea of how far away your initial point is from equilibrium in terms of the amount of energy that's given off. You have to go further in energy terms from pure products. In this case, then you have to go from pure reactants to equilibrium. So you could extract more free energy by starting with the products and going towards equilibrium. So that's just kind of something to think about, and something that we'll go over a little bit more, and you might see it in some problems. All right. Then now this plate is a weak analogy of mine that I tried to make an analogy between a ball rolling in a well and its potential energy. It's going to want to get to that minimum in potential energy, just like free energy is going to want to attain that minimum. That minimum in free energy is related to the equilibrium mixture. So I don't know if that helps at all or not, but it's kind of cheesy, and I don't know, just made it up. All right, the last thing that I want to talk about today is the signs, and then I'll let you go to think about this because we're going to be applying this over and over again. So again, I want to take a look at the Gibbs-Helmholtz equation and dissect the signs. I know that for the Gibbs-Helmholtz equation, the sign of delta G should be negative for a spontaneous process, right? And if it's positive, then I know that the opposite reaction is spontaneous. So that begs the question, what goes into making the sign of delta G? All right, if I look at this equation, I see that there's two terms or two factors. There's the delta H of the system or the delta H of the reaction. See, we dropped all the subscripts. This really is applied to our reaction. So we could have reaction subscripts here. But we don't need it because every time we use this equation, it's understood. So the two terms that go into dictating the signs of delta G is the delta H, or the exo or endothermicity of my reaction, and the delta S of my reaction. Am I going to increase or decrease entropy? Am I creating gas or a liquid or a solid from a gas, a liquid, or a solid? You know, what's happening? So I have these two terms, and I see that these two terms, the delta S of the reaction and the delta H of reaction, are going to have their own signs. And I have to also incorporate this sign here, the minus T delta S. So the question is, what are the signs of delta H and delta S have to be to dictate what the sign of delta G is, and therefore tell me if I'm dealing with spontaneous or non-spontaneous reaction. And so I have here all the four possible combinations of delta H and delta S that you'll run up against for all the reactions that you have to consider. Okay, so some reactions here are going to be exothermic, okay? And some reactions are going to be endothermic, okay? Some reactions will be accompanied by an increase in entropy, and some will be accompanied by a decrease in entropy. And so we look at these different possibilities in combination with this Gibbs-Helmholtz equation here to see what the sign of delta G is going to be. So when delta H, for example, is negative and delta S is positive, this term here is going to be negative. This term right here is going to be positive. And because this negative sign here is going to change the sign of this whole factor, delta G is always going to be negative because you have a negative term and a negative term. Does everyone see that? You guys see that? How that dictates the sign of delta G?
Yeah.
Yeah.
Okay, awesome.
Yes.
Now, once you guys see that, then all the rest should fall in line. Let's do number two. Number two says, let's consider a reaction that's endothermic. And in this reaction, entropy is destroyed or decreases. So now I have a positive term here and a negative term for delta S. Then delta G is always going to be positive and the reaction is going to be spontaneous towards reactants, not products. It's going to be spontaneous in the opposite direction. And there's nothing you can do about it. That's the way it is when you have this combination of endothermic with a decrease in entropy. In fact, these first two examples, if you run up against them for any specific reaction, then they're always going to go one way. In this case, they're going to go towards the products, and in this case, they're going to go towards the reactants. Okay. Now, that leaves 3 and 4. These guys are the interesting ones because you don't know what the sign of delta G is going to be from just the signs of delta H and delta S. Why don't you know? Does anybody have an idea?
Well, because if the temperature is a smaller number, it could be smaller than delta H and come out positive, but if it's larger, it would come out negative.
Yeah, okay, so you got it. It's temperature dependent. Remember, these two terms are weighing against each other. This term here and this term here, which has the negative in front of it. So whichever one of those magnitudes wins out, then they're going to dictate the sign of delta G and the spontaneity of the process. Okay. And so they're temperature dependent. And these are the guys that are kind of interesting. Those reactions that you have a little more power over to determine which way the reaction is going to go spontaneously. Well, it's not working. It's not going. I'm not getting any products. Well, maybe you can change the temperature. If it's case 1 and 2, forget about it. There's nothing you can do. Case 3 and 4, there is. So this gives you power over which way you can force a reaction to go, because you can change the temperature. There's nothing in case 1 and 2 that you can do. Well, I can't say there's nothing. That's not true. There's other things you can do, like changing pressure, but we're only considering standard conditions, usually only standard, and that's why we have these thermodynamic properties of delta H, S, and G with the superscript 0 for right now. Okay. And so how does this apply to something as simple as the melting of ice in this case, which is one of those situations back here that is temperature dependent? Okay. And in fact, when the signs of delta H and delta S are the same, it's temperature dependent. Check it out. When delta H is negative, it's exothermic. And when delta S is negative, it's temperature dependent. When it's endothermic, or delta H is positive and the delta S of the reaction is positive, again, it's temperature dependent. So it's only when they're opposites that you can't do anything about. But when they're the same sign, then it's temperature dependent. So let's check it out for the melting of ice. Now it says here, I got solid water going to liquid water. What is the sign of enthalpy, delta H?
Delta H will be positive.
Yeah, does that make sense? So what does it mean to have a positive delta H? What's happening?
More entropy.
Well, what is H? Enthalpy.
Sorry, entropy. Um,
It has to take in energy from the surroundings.
Okay, guys. Enthalpy, H, is associated with heat energy. That's why they put an H there. And it's also equal to Q, heat, under constant pressure conditions. So enthalpy is heat energy. It's a specific type of energy. And when it's positive, when delta H is positive, what does that mean as far as heat?
That it requires heat.
That it
Like it'll,
requires heat. Yeah, so I could put for this reaction plus heat. It's endothermic. Now, doesn't that complete your picture for this reaction? I'm going to need heat to melt ice, right? And so it makes sense that the melting of ice is endothermic. So this should not be a surprise to you. Delta H is positive. Okay? Does that make sense?
yes.
Okay, guys. If it doesn't, let me know. Now, let's look at the sign of delta S for this. What do you think the sign of delta S is going to be?
Positive.
Yeah, it's also going to be positive. Awesome. And does that make sense with our definition of entropy?
Yes, there will be more disorders on the water and liquid water.
Yeah, so it's not disorder. Remember, that's how the old textbooks used to call it. What it is, it's a spreading out of particles. Remember, that's what the measure of entropy is. It's the spreading out of particles and energy. So the particles are more spread out in the liquid state than in the solid state. And that's why liquid has more entropy than solid water. All right, great. So now we're not only taking their word for it, whoever wrote these plates, me, but we can see why delta H should be positive and delta S should be positive as well. And you need to take these quantities that are somewhat abstract, these thermodynamic quantities of H and S, look at their definitions, apply it back to the reaction at hand, and make sense of this. These things are not abstract, they mean something, and they should mean something to you. And I hope that you can see this, and maybe you can start getting used to thinking in terms of this as you deal with these thermodynamic properties and you look at reactions. So now you know, oh, enthalpy, that's heat content. Is it exo or endothermic? Entropy, well, is the energy or particles more spread out or less spread out? G, Gibbs free energy content. Oh, that's possibly the amount of work that I could do with this energy. It's an upper bound. It's a maximum amount. So you're making macroscopic connections to things that are going on microscopically, and terminology that we're using. I think it would do you injustice to just say, oh yeah, that's the definition, but I can't really connect it to the problem at hand or what's happening in the reaction. You're short selling yourselves. There's a lot of deeper understanding here that you can, take to your next level or your next class. And I don't want you to miss it. All right, so we're bringing meaning to this reaction. And now we want to see how temperature might affect the values of delta G. All right, the first thing says at 0 degrees Celsius. Now, of course, we have to convert that to Kelvin because that's what, for example, that's what the units of entropy is in. Enthalpy is in usually like delta H's are in units of joules per mole. Delta S's, remember, are in units of joules per mole Kelvin. So there's a temperature involved here. And then, of course, delta G, most of the time they put them actually in kilojoules per mole for delta G and H. And entropy is in joules per mole, usually, if you look in your textbook. Anyway, we want to look at this temperature, 273. Now we know it's 0 degrees. What takes place in this reaction at 0 degrees? Is there a net conversion of liquid to ice or ice to liquid at 0 degrees, right at 0?
Liquid to ice.
So at 0 degrees, would ice melt or would water freeze?
Water
Isn't
would freeze.
This is awesome, you guys. Neither one, right? It's right at the transition temperature. So one is not preferred over the other. You're right at the freezing point. So isn't that equilibrium? Yeah,
Yeah.
it is,
Mhm.
right? That's right at equilibrium. That's this shot down here. Okay. So right at 273, that's what I was talking about. So right at 273 or 0 degrees, there's an equilibrium between the liquid and the solid. That's the equilibrium temperature. And so we know that at equilibrium, delta G is going to be 0. There's, you don't get any more energy out going one way or the other. That's the minimum of energy at that equilibrium. And so that must mean that the positivity of delta H is completely erased by the increase in entropy that's created. So these terms in our Gibbs-Helmholtz, this term and this term, have the same magnitude but opposite in sign because of this. And so they wipe out each other, and it's equilibrium at 0 degrees. And we know that's true for water. Now, at temperatures less than 273 degrees, that means this value here for temperature is smaller now. So that means that this term is smaller than this term and opposite in sign. So this wins out, the delta H, the positivity of the delta H wins out, makes delta G positive, and temperatures lower than 0 degrees make the opposite reaction spontaneous. And we do get a net amount of liquid water to freeze and form solids. Does that make sense?
Yes.
Okay, see how we're playing around with these signs, but we're playing around with them by looking at a specific example of ice melting to liquid water and the signs of delta G, that it's dictated by the signs of delta H and delta S, because in this process, we know that it's temperature dependent because both of them are positive. And that's what we said would happen back here. When both are positive, they're temperature dependent because the magnitudes of delta S and delta H are important because they're going to fight against each other, or they got to be weighed up against each other. And what does that mean if we go one step back and look at the second law of thermo? This term here, this delta H term, the exo or endothermicity of the reaction, that's really speaks to the entropy that's created or destroyed in the surroundings. That's an important term. All right. And then we can look at the other possibility, and that's the possibility where the temperature is greater than 0 degrees Celsius. And we know when the temperature is greater than 0 degrees that ice melts. And sure enough, if we put in our signs and we say, okay, now this term here at temperatures greater than 0 degrees or greater than 273, temperatures getting larger, this term's going to outweigh the positivity of delta H, make delta G negative, and make the melting of ice spontaneous at higher temperatures. Does everyone see that?
Yes.
Any questions on that? No? All right, well, I think it's important to go through a simple reaction and rationalize the signs in terms of the sign and spontaneity of delta G, therefore. So take your time with that and think through those signs because we'll be using them again. Now, also, this Gibbs-Holtz equation can be used, and it was implied in this last exercise, right? So we know that delta G equals delta H minus T delta S. So we know that we can talk about equilibrium, and when this term here exactly balances out this term, that's equilibrium, because then delta G will equal 0. Well, can't we put in a 0 and calculate a delta S for a reaction using the tabulated values, calculated delta H for a reaction, put that in here, and then find out what temperature, what T needs to be for equilibrium. Or in other words, we can find transition temperatures. And that's what this next problem is. And this next problem deals with. And I'll just take you through this kind of quickly, and then you can go back and study it. And we'll talk about it next time in detail. But essentially, here we have another reaction. This is rust, iron oxide, and iron. Now, just look at this equation. Does rust naturally form from iron, or do we get iron naturally from rust? I.e., which way is this going to take place naturally? Is it going to go from left to right naturally, or from right to left? What do you think?
Right to left.
Right to left.
That's correct, right? Because that's what we see in nature. Iron rusts naturally. So you're expecting, when you calculated delta G for this reaction, what are you expecting the sign to be?
Positive.
Positive. Boom. All right, I think that's a good spot to stop. You can look at the rest later, and then we'll pick it up next week right here.
All right, thanks, Professor.
All right, guys. Anybody have any questions? You can hang out, and we'll go over them specifically.